Welcome to aminacademy.com. In fluid mechanics, let us discuss about flow of viscous fluid through a circular pipe. A fluid which are viscous and flowing at very low velocity. At low velocities, the fluid moves in layers. Each layer of fluid slides over the adjacent layers. Due to relative velocity between two layers, the velocity gradient first velocity gradient equal du by dy. Shear stress to equal mu into du by dx, du by dy. The flow through the circular pipe will be viscous or laminar. If the Reynolds number R is less than 2000, the expression for Reynolds number is given by R equal to rho Vd by mu. Now, here Reynolds number R equal rho Vd by mu. Here first rho equal density of fluid. Density of fluid flow through the pipe. V equal average velocity of fluid. Then D equal diameter of pipe. Mu equal viscosity of fluid. Here look at this figure. Here through the pipe, viscous fluid is flowing through this direction. Here r equal radius of the pipe. We are taking small elemental cylindrical fluid with radius r and length delta x. This radius of pipe r equal to radius of pipe. Then consider a small fluid element. Small fluid element. Radius r. Radius r sliding in a cylindrical fluid element. Sliding in a cylindrical fluid element. Element of radius r plus r. Of radius r plus dr. Now length of fluid element equal to delta x. If P is the intensity of pressure, P is intensity of pressure on the face AB, here here the face AB is here and CD is this side. Intensity of pressure AB, pressure side AB, and P plus dou P by dou X into dx is the pressure intensity at the face CD. The pressure force P into pi r squared on face AB. The shear force, third one, the shear force, that is tau into 2 pi r dx through the circumference of the fluid on the surface of the fluid, on the surface of the fluid. These are the three forces acting inside the liquid which is flowing. Therefore, we are equating the things of now considering these three forces, like here P into pi r squared minus P plus dou P by dou x into delta x pi r squared minus 2 into 2 pi r delta x equal to 0. Now which gives minus dou P by dou x delta x pi r squared minus tau into 2 pi r into delta x equal to 0, which gives minus dou P by dou x r minus 2 tau, because we are cutting the common terms, equal to 0. Therefore, tau equal minus dou P by dou x into r by 2. Therefore, this is shear stress. Let it be 1. Now, the shear stress tau across a section varies with r, as dou P by dou x across the section is constant. Hence, the shear stress distribution here, this is a shear stress distribution. Here, this velocity distribution here, this shear stress distribution is a triangular and velocity distribution is a parabolic. Now first we'll consider velocity distribution. Velocity distribution velo to obtain the velocity distribution across a section, the value of shear stress tau equal shear stress tau equal mu du by dx in substitute in y. Substitute in 1. Substitute in 1. So but the relation tau equal mu du by dy, y is measured from the pipe wall. Then here for y equal r minus r and dy equal minus dr. Here r is a constant. Pipe radius is constant. Therefore, tau equal mu du by du minus dr equal minus mu du by dr. Now both will substitute in, one will get, therefore minus mu du by dr equal minus dou p by dou x into r by 2. We are substituting in equation 1. Or we have du by dr equal 1 over 2 mu dou p by dou r into r. Now we are integrating both sides, that is du equal 1 by 2 mu dou p by dou r, dou p by dou r r dr, r dr equal, we have u, integrating du get u 1 by 4 mu dou p by dou x here, dou p by dou x into r squared plus constant of integration c, where c is the constant of integration and its value is obtained from the boundary condition at here boundary condition r equal to r, that is radius is extreme, that is capital R, and at near the wall, that is the boundary touch the wall of the pipe, velocity is 0. Therefore 0, we are substituting above 1 by 4 mu dou p by dou x into r squared plus c. Therefore c we have minus 4 mu dou p by dou x into r squared. Therefore substituting the value of c in here u value. Therefore u equal 1 by 4 mu dou p by dou x r squared minus 1 by 4 mu dou p by dou x r squared. So which give u equal 1 by 4 mu dou p by dou x r squared minus r squared, because the minus value. Yeah, therefore we got the velocity of the fluid. Here mu and dou p by dou x and capital R are constant, which means the velocity u varies with the square of r square. Then second one, ratio of maximum velocity to ratio of maximum velocity to average velocity. Average velocity. Here the velocity is maximum when r equal to 0. When r equal to 0, the velocity become maximum. Therefore u max equal minus 1 by 4 mu here u max equal to minus 1 by 4 mu dou p by dou x r square. That is maximum velocity at the center of the pipe, because r is small r is 0. Then average velocity we can keep u bar. We can get average velocity u bar is obtained by dividing the discharge of the fluid across the section by the area of the pipe by r squared. Therefore now dq, that is fluid flowing per second in elementary ring, that is dq, which is equal velocity at radius r and circumference 2 pi r dr. So we use this u as already 1 by 4 mu dou p by dou x r squared minus r squared into 2 pi r dr. Therefore integrating we'll get q equal 0 to r dq, which is equal 0 to r minus 1 by 4 mu dou p by dou x r squared minus r squared dr, 2 pi r dr, 2 pi r dr. The constant comes out of integration, that is 1 by 4 mu dou p by dou x into 2 pi, so 0 to r, the remaining things is r squared minus r squared r dr. Then further this gives 1 by 4 mu dou p by dou x into 2 pi 0 to r. Here r is multiplied here, that become r square r minus r cube dr. Here then, so we get, after putting this 0 to r, integrating, r squared by 2, r cube is r4 by r. So we'll get final average velocity u bar is, no, before that we'll find the q in simplified manner. Here discharge q equal pi by 8 mu minus dou p by dou x into r power 4, after integrating and substituting r values. Therefore average velocity is u bar equal q by area, that is pi over 8 mu minus dou p by dou x r power 4 over pi r squared. After simplifying, we get u bar equal 1 by 8 mu minus dou p by dou x r squared, because pi cut, r squared cut with r power 4. Then we'll find the ratio u max by u bar, maximum velocity with average velocity, that is minus 1 by 4 mu dou p by dou x r squared over 1 by 8 mu minus dou p by dou x r squared, which gives 2. Next is pressure drop. For a given length, L. Then you have u bar equal 1 by 8 mu minus dou p by dou x r squared, or here dou p by dou x equal 8 mu u dash over r squared. Now integrating this equation with respect to x, minus integral, suppose 2 to 1, the section 1 and 2, that is dp equal 2 to 1 8 mu u bar over r squared dx. So we have minus p1 minus p2, pressure drop between section 1 and 2 is equal 8 mu u bar over r squared x1 minus x2 by integrating this right side. Therefore we can tell p1 minus p2, which the minus go this side, will get 8 mu u bar over r squared x2 minus x1. So here x2 minus x1 will keep it L, that is 8 mu u bar r squared into L. So further 8 mu u bar r can be written as d by 2, that whole square L. So we have P1 minus P2 is head loss, we can keep it HF. Loss final values are 32 mu u bar L over rho G then we can use it. HF is pressure drop is P2 minus P1 by rho G, means head loss due to the flow of viscous fluid. Therefore we get, therefore HF equal P2 minus P1 by rho G equal 32 mu u bar L by rho G d squared. Here this is called Hagen Poiseuille. Hagen Poiseuille formula for viscous flow. We have done. Please subscribe our YouTube channel.